All right, we're going to begin chapter 4, section 1, where we discuss or introduce rational functions and asymptotes. All right, this is what the graph of a rational function looks like, right? Now, we've talked about rational functions before. A rational function is just another word for a fractional function, right? So you have a fraction, right? So you have x in the denominator or any variable, right? So this is probably as basic as a rational function will get, right? And this is what the graph looks like, right? Kind of a strange shape that you guys maybe haven't seen before. But it takes this shape, and if you really wanted to verify what that shape looks like, you could just make a table of values, right? So if you made a little table of values, x, f of x, and you start plugging numbers in, right, you're going to see that it's going to make this shape. And the reason why it has this weird little curved behavior is because we know that if we were to plug in 0, right, we get 0 on the bottom, which is undefined, right, which actually has some meaning in our graph, right? You're going to see that if you zoom in super, super close, you're not going to ever touch that 0, right? Because, again, you can't have a real defined function value at 0. But you can get really, really close to 0, right? And then you can see that as you get really, really close to 0, right, the y value is going to go up, right? You see that we're getting up, but there's still this little gap, right? You see that there's a little bit of a gap there. And that gap is always going to exist, all right? And that introduces something that we call an asymptote, right? And it also introduces the concept of a limit, right? You guys aren't really going to see limits until you guys get to calculus, right? I would hope that that's somewhere in your future, right? Especially if you're a sophomore or a freshman, that hopefully, I would hope that you guys get the chance to take a calculus class, because it really ties everything that we're doing together and puts it into greater mathematical context, right? But let's just say, right, we introduce the concept of a limit, right? Really, the notation here isn't super proper. You would really say the limit as x approaches 0 from the right, right? If you plug in numbers that are close to 0 on the right into f of x, you're going to get a positive infinity, right? And you can see that because it's going up, right? Up, right? And similarly, if I have the limit as x approaches 0 from the left, and I plug those numbers into f of x, then we get negative infinity, right? You see that we're going to go way down here, right? You're going way down to negative infinity, all right? So this little line right here that we're approaching but never really touch, right? So I'm coloring it in blue right here. This is what we call an asymptote, all right? So I'll even write that down for you guys. An asymptote is a line that we approach but never touch. All right? We approach it, but we never touch it. All right? Sometimes you can cross it, right? Vertical asymptotes you can never cross. We'll talk about that in the next slide. Horizontal asymptotes, sometimes you can cross, but as you go towards, or as you tend towards a certain value, right, it's going to get really, really close to that line, right? And you can see, if I were to zoom out, right, I wish I could show you guys, right, but probably in class when I show you guys this, I'll open up a Desmos graphing calculator, and then I'll show you guys, as you zoom in super, super close towards 0, then you get really, really close, or I'm sorry, you go really, really up, right, towards infinity. You have a similar behavior happening as you go more and more to the left and to the right, right? You see that as you're going to the right, there's still this little gap right here, all right? And you approach the x-axis, right? Similar thing happening over here, right? As you go all the way to the left, right, you're going to see that we're still approaching the x-axis, right? There's still a little bit of a gap there, but you're never quite touching it, right? That represents a horizontal asymptote, right? So this, what I wrote in blue, is a vertical asymptote. Here, what I'm writing in red, this is a horizontal asymptote, right? You're approaching it, but you're never touching it. Again, in limit definition, which you guys are going to see in calculus, you can say the limit as x approaches positive infinity of f of x. So meaning if you plug in really big numbers into our function, you're going to get a number super close to 0 that we could say the limit as it approaches infinity is 0, right? Similarly, if I say the limit as x approaches negative infinity, if I plug in really big negative numbers into our function, we also approach 0, right? Again, these definitions you don't need to really know for the sake of this lesson, but it's helpful that when you guys get to calculus and even in pre-calc, right? Those of you that are doing AP pre-calc or pre-calc honors advanced next year, towards the end of the school year, right? End of fourth quarter, you're probably going to see some definitions of limits, right? And kind of introduce calculus topics, all right? But that's what the graph of this looks like. For the sake of this lesson, we're only really going to discuss the asymptotes and the behavior as it approaches these imaginary lines. All right. So again, I said the vertical asymptote is the imaginary vertical line. So maybe something like that your graph approaches but never touches, right? Again, it can go super, super close, right? Maybe something like that. And then it'll level out and then maybe go super, super close, something like that. Right, so that's an example of a vertical asymptote. And to find what that is, to find where that imaginary line is, all you have to do is set the denominator equal to 0. All right, because if you make that observation from the previous slide, we have an undefined value at that particular value of x. So if I had, let's say, 1 over x plus 2, if I set this equal to 0, I know that x equals -2. This is the equation of a line, a vertical line, right? So then I have at x equals -2 a vertical line that we're never going to cross, right? Only get really, really close to, right? So you cannot cross the vertical asymptote, all right? With horizontal asymptotes, right, again, that's going this way, right? We're getting super, super close to it, right? Maybe something like that and like that. Again, we'll get to graphing these in the next lesson, all right? But we might get super, super close to this horizontal line. You can cross it. Some functions, you will have some strange behavior happening in between the left and right of it. You can cross it. To actually figure out what the horizontal asymptote is going to be, you have 3 scenarios, right? So it's these 3 scenarios, right? 1, 2, and 3. Right, so for the sake of the horizontal asymptote, let's just say the letter n is the degree of the numerator and m is the degree of the denominator, right? If you have the degree on the top is less than the degree on the bottom, then you have a horizontal asymptote at y equals 0. So the x-axis, basically, right? So for example, if I have like x over x squared minus 2, all right, the degree on top is 1. The degree on the bottom is 2, right? The degree on top is less than the degree on the bottom, so we have a horizontal asymptote at y equals 0, right? That's the only possibility for these particular kinds of functions, right? If I have that n is greater than m, so for example, let me flip it. Let's say it was x squared minus 2 over, x plus 1. Right? On the top, our degree is 2. On the bottom, our degree is 1. Then you don't have a horizontal asymptote, right? None, right? You don't have one. But what you have instead is a slant asymptote, right? And that's right here, right? We'll talk about that in a second, all right? But that is a slant asymptote. If you have the degree on the top is the same as the degree on the bottom, so let's say it was, I'll use the same one, x squared minus 2 over, I'm going to say 2x squared minus 1. All right. Notice that this 2 on top is the same as this 2 on the bottom, right? They have the same degree. Your horizontal asymptote is going to be the degree on top. The leading coefficient on top, which is 1, over the leading coefficient on the bottom, so 2. Right? So you just take the leading coefficients and you put them in one on top of the other, all right, and then you get that as your asymptote, all right? And then now let's talk about the slant asymptote. So the slant asymptote exists only if the numerator is 1 more than the degree of the denominator. all right? And to actually find out what it is, you divide, so long or synthetic. So long or synthetic, I like to do long division just because you get your answer right away, right? So you would divide it, and then you would set the quotient equal to y. So you would get like a line equation. You would get like a y equals mx plus b type of equation, and then you ignore the remainder, right? You might have a remainder, chances are you will, but you don't have to look at it. You only look at the quotient to find out your slant asymptote. All right, now let's say your rational function does simplify, right? So let me give you guys something like x squared minus 9 over x plus 3. Well, you guys know that x squared minus 9 is a difference of squares. That's the same as x plus 3, x minus 3. And then on the bottom, I have the x plus 3. Notice that you have something that cancels out, right? X plus 3 cancels out, and you're left with x minus 3, which to you guys, that's just a simple line, right? I get like a regular line, maybe looks something like that with a y-intercept at -3. But there is a value that made the bottom equal to 0, right? So if I set the bottom, the original bottom equal to 0, I get x is -3. At -3, I'm going to get a hole, meaning that I'm going to have a little open circle in the middle of our line, right? So it sets it apart from a normal line, right? They're not always going to look like this. You'll probably have like actual curves the way that we did before in the first slide that I showed you guys. But that's just an example of this sort of discontinuity, right? That's what we call a hole. In calculus, you'll probably learn that this is also called a removable. All right, I'm spelling removable wrong. Removable. Right, a removable discontinuity. Meaning it makes our function discontinuous at a certain value, right? So that's an example of a discontinuity. There are other types of discontinuities, like the asymptote that we have discussed, right? But this is called a removable one, right? Meaning you are able to cancel it out. You just get a value that makes it undefined, right? Somewhere in the middle of your function, all right? And that's what we call a hole, right? So a hole exists if you can simplify the function by crossing out a factor, all right? And you always give your hole as an ordered pair x comma y. And to actually find out where the hole is going to be, x is going to be whatever you crossed out. So in this case, it's -3. And you get the y value from plugging that in to your simplified equation, right? If you just plug it into the original, you're going to get undefined, right? Because that's the point of it being a discontinuity, a hole, all right? So you're going to plug it into the simplified equation. So for the sake of this, it's going to be -3, -6, all right? We're going to have a little hole there at that point, all right? And that's what we mean when we say a hole. Again, that's going to make more sense when we start graphing these, but for the sake of this lesson, you just need to know how to find it. All right, so we're going to, for these first few examples, find the horizontal, vertical, or slant asymptotes. All right, so first, to find, the easiest thing to find is a vertical asymptote. So I'm going to abbreviate that VA, right? To find the vertical asymptote, and let me actually write this on the side, vertical asymptote, you have to set your denominator equal to 0. So your vertical asymptote for number 1, it's going to be x minus 1 equals 0. And then so we end up with x equals 1, right? And that's our vertical asymptote. So meaning at x equals 1, we're going to have a little dotted line or an imaginary line that we're going to approach but never cross. All right. Next thing that we want to try to find is the horizontal asymptote. So again, the horizontal asymptote, there are 3 cases. All right. So case number 1 is it's going to be y equals 0. Case number 2, it's y equals leading coefficient of the numerator over the leading coefficient of the denominator. And then the third case is it's going to be none, where in this case you might get a slant asymptote. All right. Now it's y equals 0. when, hopefully you remember, the degree of the numerator is less than the degree of the denominator. All right, and it's the leading coefficients if the degrees are equal. So degrees are equal. And it's none, it has a slant if the degree of the numerator is greater than the degree of the denominator. All right, so let's take a look at this one. All right, the degree on top, all right, our degree is 0, right? If it's just a constant, your degree is 0. And then on the bottom, your degree is 1, right? If I just see an x, you assume that it has an exponent of 1. So in this case, the top is less than the bottom, right? 0 is less than 1. So I know for sure I'm going to have a horizontal asymptote at y equals 0. All right, don't need to do any math for that. All right, just need to know that the degree on top is less than the bottom. And if it has a horizontal, it doesn't have a slant asymptote. All right, and that's all we have to do for these problems. All right, let's try the exact same thing over here. All right, again, all you have to do, the first thing, I want to try to find the vertical asymptote. That's probably the easiest thing to find. Set the bottom equal to 0. Now when you set the bottom equal to 0, subtract 2, we get 3x is negative 2. Divide by 3, and I get x equals negative 2/3. All right, and then so we have an imaginary line at negative 2/3, at x equals negative 2/3. All right, let's do the same thing with a horizontal asymptote, right? Let's check our 3 cases, right? There's 3 cases to be aware of. The degree on top is a 1, right? Exponent of 1, and the degree on the bottom is also a 1, right? If the degrees are the same, you take the leading coefficients. So it's going to be y equals the leading coefficient on top is a 2 over the leading coefficient on the bottom is a 3. So I have an imaginary line at y equals 2/3. And if I have a horizontal, I don't have a slant. All right? Good. All right, let's try the exact same thing with the next one. So hopefully you see it's not too bad. All right, so I'm going to start with the vertical. That's the easiest thing to start with. Set the bottom equal to 0, and we get x is negative 2. So I have an imaginary vertical line at x equals negative 2. For the horizontal asymptote, check the degrees. All right, the degree on top is a 2, on the bottom is 1. Okay, so a little bit different, right? 2 is greater than 1. So that means I'm not going to have any horizontal asymptote. So that means I'm going to have a slant. To find the slant, do longer synthetic division, right? So I'm going to do x plus 2, and then I'm going to have an x squared plus, right? I always tell you guys have a placeholder, 0x plus 1. And now let's see, right? Multiply by x. X times x plus 2 is an x squared plus 2x. Subtract everything, and then we end up with a negative 2x. Bring down the 1, I get a plus 1. And then I need to multiply x plus 2 by negative 2 to get that negative 2 out of there. And then we don't need to do anything else from here, right? You could figure out what the remainder is, but we don't care what the remainder is. The slant asymptote is only going to be this part of it, right? You never want to look at the remainder. So the slant asymptote is going to be a y equals mx plus b type of equation, and it's going to be x minus 2. All right, on a graph, what this would look like is you would graph this line, the x minus 2, right? And you guys know that that's a line that maybe looks something like that, right? So you'd get that imaginary line combined with our vertical asymptote at negative 2, right? It might be something like that. And then we get like a little curve that maybe boomerangs, something like that. All right, that's just my guess right now, right? It might look different. It might actually go in the other direction, right? So it might look something like that or like that, right? But again, we'll get to graphing in the next slide. I mean, not in the next slide, the next lesson. All right, but that's for now what you can kind of guess what the graph would look like, and that's what it would look like in context. All right, same instructions as before, just this time we're going to have to check for holes. All right, now checking for holes, that's an indication that we're going to have to factor, right? So I tell you guys, the vertical asymptotes are typically the easiest thing to check for first, but if there's possibility of a hole, then you want to make sure that you're factoring first, because you don't want to accidentally count a vertical asymptote as a hole or I'm sorry, vice versa, right? You don't want to count a hole as a vertical asymptote when really it cancels out, right? But if you look at the first one, right, nothing really factors here, right? So we don't have to worry about holes, right? If nothing factors and nothing cancels for holes, I'm going to write none, right? Cannot be factored. That doesn't always mean that when it can be factored, you're going to have a hole. It's just when your factors cancel, you have one. All right, but for the sake of this, I'm going to start with the holes. All right, holes, I have none. And now let's move on to the next best thing, which is the vertical asymptotes. All right, set the bottom equal to 0. So I'm going to do 3x squared plus 1 equals 0. All right, when we subtract 1, we get 3x squared equals negative 1. Divide by 3. We get x squared equals negative 1/3. And then you're going to have to end up square rooting a negative, which is going to leave you with an I somewhere in your answer, right? I don't even have to evaluate this fully. Just recognize I in your answer is not going to give you any real line. It's going to give you a line in the imaginary plane, right? But we're only graphing in the real number plane, right? So we're going to have no vertical asymptotes either, right? That's fine. Not always are you going to have one, right? Sometimes you don't. Let's move on to the horizontal asymptote, right? The horizontal asymptote, you're looking at the degrees, right? The degree on top is 1. The degree on the bottom is a 2, right? 2x to the first and 3x to the second, right? If the top is smaller than the bottom, that's only one scenario, it's y equals 0, right? Only one possibility there. And if there is a horizontal asymptote, there is no slant asymptote. So here I'm going to write none, all right? That's all we have to do for that one. Let's do the same thing with the next one. Again, I always check for holes. Well, I had told you guys typically I always check for the vertical asymptotes. If it does factor, though, you want to check for holes. And you notice the bottom here does factor. All right, it becomes an x plus 1, x minus 1. All right, under the 2x squared. But notice that when you do this, nothing cancels out, right? If nothing cancels out, you don't have any holes. Holes, I'm going to say none. Again, I'll write a short little explanation. You're never going to have to do this, but just so that you guys have for your notes, right? No factors canceled out. No factors canceled. All right. So if there are no holes, let's move on to our asymptotes. All right, let's start with our vertical asymptotes. All right, let's set the bottom equal to 0. All right, I would use the factored one just because that helps you a little bit better. And then you get two vertical asymptotes here. You get x equals negative 1, and you get x equals 1. All right, so this time there are two vertical lines that you're going to approach but never cross or never touch, right? And now let's do something similar for the horizontals, right? The horizontal asymptote, you're looking at the degree, right? The degree on top is 2, right? It's a 2x squared. The degree on the bottom is also a 2. It's an x squared. So this is the only other scenario where you're going to have to check for the leading coefficients, right? On top, it's a 2, right? Over on the bottom, the leading coefficient is a 1. So 2 over 1, which is just 2, right? So this is going to get us, a horizontal asymptote of y equals 2, all right? So there's our horizontal asymptote. If you have a horizontal asymptote, you don't have a slant, all right? Excellent. Let's try the same thing with the next one. All right, let's try first to factor, rule out any holes, right? So what I'm going to do is factor, right? The top factors as x plus 2, x minus 1. And the bottom factors as x plus 2, x minus 3. And now notice something happens here, right? Notice what cancels out. The x plus 2's cancel out. So then I know for sure I'm going to have a hole. All right. Our simplified expression is x minus 1 over x minus 3. And the value that canceled out is x equals negative 2, right? If I set this factor, the one that canceled out, equal to 0, you get negative 2. So I know I'm for sure going to have a hole at an ordered pair of negative 2 comma something. To figure out what that something is, plug in negative 2 into the simplified expression. So we end up with a negative 2 minus 1 over negative 2 minus 3. And that's going to get us a negative 3 over negative 5, which is a positive 3 over 5. So I get negative 2 comma 3/5 as the whole. So that means on this graph, I'm just going to do a little sketch right here. On our ordered pair, on the ordered pair negative 2 3/5, right? I'm just going to say that somewhere right there. I'm going to have a little hole. I don't know what it's going to look like outside of this, but let's just say it looks like that. I'm just guessing, right? It might not look like this at all, right? But just as an example, that's what the hole would look like on your graph, right? It would literally just look like your normal curve, just you would need an open circle at that point, all right? All right, so there's your hole. This time we did have one. All right, to find your other information, all right, let's say you now want to find the vertical asymptote, right? After you have your hole, you cannot use it again, right? I can't say that it's x equals negative 2, even though that does make the bottom equal to 0, right? I can't use it because it was a hole, right? So I would only use the other one then, right? In this case, the only other thing on the bottom was this x minus 3. And setting that equal to 0, I get x equals 3. I only get one vertical asymptote here, all right? Next thing we need to figure out is the horizontal asymptote. Here, check out the degrees you're going to do of the original, right? You're not going to do the simplified one, right? The original, your degree was a 2 on the top and a 2 on the bottom. So it's going to be the leading coefficients. The leading coefficient on top is a 1, and on the bottom it's also a 1. 1 over 1 is just 1, right? And if you have a horizontal, you don't have a slant. So never are you going to have all of these, every single one of them, all right? You're going to have a couple of them, but never are you going to have all of them. You might have all but one, right? But if you have all of them, right, you should probably double check your work, right? Maybe you made a mistake somewhere. All right, good. All right, last one on this page. Let's try the same thing. Let's try to figure out if there are any holes first, and to do that, we're going to have to factor. All right, looks like the top is going to be a trinomial where a is not equal to 1, so I need factors of 3 times negative 6 is negative 18. So I need factors of negative 18 that add to a positive 7, and that's going to be a 9 and a negative 2. Right? And then when you do the math over here, this is going to be an x plus 9, x minus 2, and then you have a 3 in front, so make sure you're dividing by that 3. And then you're going to go ahead and slide and divide, right? So this is going to get you x plus 3 and 3x minus 2 over, and then the bottom is going to factor as an x plus 1 and an x plus 3. Once again, we do have something that cancels out, right? So the x plus 3 and the x plus 3 cancel out. That leaves our simplified expression as a 3x minus 2 over x plus 1. All right, so I'm going to have for sure a hole. All right, we're going to have a hole at an x value of negative 3. Right, how did I get that number? Well, take whatever was canceled out, x plus 3, and set that equal to 0. Right, x plus 3 equals 0. And then you get x equals negative 3. So I know for sure the x coordinate is negative 3. To figure out what the y coordinate is going to be, you're going to plug that into the simplified expression. So this is going to be a 3 times a negative 3 minus 2 over negative 3 plus 1. All right, let's see what that gets us. That gets us a negative 9 minus 2 over negative 2. So negative 11 over negative 2. And that's going to get you simplified 11 over 2. So I'm going to have a hole at negative 3 comma 11 halves, right? So something like that. To figure out the vertical asymptote, we also use the simplified expression, right? I don't want to count x equals negative 3 because that one was part of our hole. So what you're going to do is you're going to take the bottom of the simplified expression, set it equal to 0, and then you end up with x equals negative 1. So we only get one vertical asymptote here. All right, to find the horizontal, all right, what you're going to do is look at the original, look at our leading coefficients if the degrees are the same, right? In this case, they are, right? The 2 and the 2. So that means I'm going to have a y equals 3 over a 1, which is just going to get you a y equals 3. And if there's a horizontal, there's no slant. All right? So Maybe at first the process seemed a little tedious. Hopefully you guys are seeing that it's getting a little bit better, as assuming you follow the steps in this order, right? You don't want to make sure that, you want to make sure that you're not making mistakes, especially with your vertical asymptotes and the holes, right? That's typically where the mistakes come from. All right, now let's finish up with these examples. All right, so again, same directions as before, find the asymptotes, check for holes. All right, this first one, it's actually, the top and the bottom are not in standard form, so that might throw some people off, right? So just to make sure that we're not making any sort of mistakes, I'm just going to rewrite it in true standard form, right? So I'm going to have a negative 7x plus 3 on top, and then a 2x plus 3 on the bottom, right? And now let's look at this, right? This is exactly the same. I didn't change anything about this one other than the order of the terms, all right? So I'm just going to look at this one for now. Notice that the top and the bottom cannot be factored, so we're not going to have any holes, right? So for holes, I'm going to say none, all right? And now if there are no holes, it's going to be pretty easy to check for the vertical asymptote, right? Just set the bottom equal to 0, right? So 2x plus 3 equals 0. Then you get 2x equals negative 3. Right? Divide by 2 on both sides, and we get x equals negative 3 halves. All right? And now let's try to find our horizontal asymptotes, if any, right? Now the degree on top is a 1, the degree on the bottom is a 1. So that means, just like before, I'm going to need my leading coefficients. It's going to be y equals negative 7 over 2, right? Negative 7 was on top, 2 is on the bottom. And if I have a horizontal asymptote, I don't have a slant. So I'm going to say none, all right? That's all the information we need there. Let's try the same thing with this one, all right? Again, first thing I want to check is if there are any holes, right? So let's try to factor, right? The top doesn't factor, but the bottom does. It becomes x plus 3, x minus 3. All right, and then you're going to see that the x plus 3 cancels out. So that means I am for sure going to have a hole at the value that canceled out was negative 3. So it's going to be negative 3 comma something. To figure out what that something is, use the simplified expression. It's going to be 1 over x minus 3. I'm going to plug in a negative 3 in there, and that's going to get me a 1 over negative 3 minus 3, which is negative 1/6. So I'm going to have a hole on my graph at negative 3 comma negative 1/6. All right. I'm also going to use the simplified expression to find my vertical asymptotes, right? I'm going to set the bottom of the simplified equal to 0, and then I'm going to get a vertical asymptote at x equals 3. All right, now let's find our horizontal asymptotes. All right, again, you're looking at the degrees of the original, right? The original, I had a leading coefficient. I had a degree of 1, and on the bottom we have a degree of 2. Right, the top is smaller than the bottom, so there's only one scenario for this. It's y equals 0. And again, if there's a horizontal, there's no slant. All right, let's try the same thing with the next one. Again, just more factoring, more of the same stuff, right? Let's check if there are any holes. All right, the top is going to factor as a difference of squares. It's going to be an x plus 2x minus 2. Over the bottom is going to become x minus 2, and it's an x minus 1. All right, and we do have something that cancels out. And at the value that canceled out, if you do x minus 2 equals 0, then I get x equals 2. All right, so I know it's going to be 2 comma something. To figure out what that something is going to be, plug it into the simplified expression, x plus 2 over x minus 1. I'm going to plug in 2 there, and that's going to get me a 2 plus 2 over 2 minus 1, which is a 4 over 1, so 4. So I'm going to have a hole at 2 comma 4. And now from there, it's pretty easy to find my vertical asymptote. I'm going to set the simplified denominator equal to 0, and then we get x equals 1. All right. Now let's check for our horizontal asymptotes. All right, look at our degrees. The degree on top is a 2. On the bottom is also a 2, so I need my leading coefficients. It's going to be y equals 1 over 1. In this case, it's just 1. And if I have a horizontal, I don't have a slant. right? So hopefully you're seeing, right, these are getting pretty repetitive, right? And if you're good with this lesson, it's really going to help you with the next lesson when we actually start graphing these, all right? Now, once again, let's factor. The top is going to factor as an x plus 2x minus 1. And then on the bottom, again, you can do first times the last, and I'm going to do that off to the side just so it doesn't take up too much room. All right, so let me try that over here, right? We need factors of 4 that add to a 5, and it's going to be a 4 and a 1. And that's going to be x plus 4, x plus 1. There's a 2 in front, so let's divide by that 2. And then we slide and divide. So this is going to get us an x plus 2, a 2x plus 1. And then we're going to see that the x plus 2 cancels out, so we do, in fact, have a whole. Right? And that's going to be at an x value of negative 2. So it's going to be negative 2, comma. I need to know what the simplified expression is. It's x minus 1 over 2x plus 1. And I'm going to plug in negative 2 into that simplified expression. So it's going to be a negative 2 minus 1 over 2 times negative 2 plus 1. And that's negative 3 over negative 4 plus 1, which is negative 3 over negative 3, which is 1. All right, so it's negative 2 comma 1 as the whole. And now let's figure out what the vertical asymptote is going to be, right? Set the bottom of the simplified equal to 0, and then we get 2x equals negative 1. Divide by 2, and I get x is negative a half. So then my vertical asymptote is x equals negative a half, right? Horizontal. Let's check the degree. The degree on top is a 2. On the bottom, it's also a 2. So it's going to be our leading coefficients. Leading coefficient of the top is a 1. On the bottom, it's a 2, so it's going to be y equals 1/2. If you have a horizontal, you don't have a slant. All right? And that's it for this lesson. All right? So we're going to apply this knowledge into the next lesson where we actually start graphing these. Right? But hopefully you see, right? They get pretty repetitive, and once you got this part down, then honestly graphing it should not be super challenging, right?